Okay, we're at section 8.2, analysis model, isolated systems, energy. So the energy of isolated systems. So a common scenario is that no energy crosses the system boundary by any method. Consider the figure, the book Earth system. You lift the book, you get gravitational potential energy stored in the system. You calculated from the work done by the external agent on the system using work equals the change in potential energy, lifting it up. Imagine dropping the book from a lifted position. It's the dark blue physics book, not the faded one. The book Earth system does not interact with the environment. Your hand is no longer in contact with the book. As the book falls, the kinetic energy of the system, due to the motion of the book alone, increases, and the gravitational potential energy of the system decreases. So the change in kinetic energy plus the change in gravitational potential energy is equal to zero. As the potential energy decreases, you get a commensurate increase in kinetic energy. So the left side, on the left side of the equation, the sum of the changes of energy are stored in the zerom have to equal zero. No transfers of energy of any kind across the boundary of the system. So the right side equals zero. The book Earth system is isolated from the environment. The equation is valid for systems with any type of potential energy for isolated systems. So any type of potential energy could be spring potential energy. So notice the only difference with that and the equation above is the removal of the G, which is specific for gravitational potential energy. But spring potential energy would work just as well. Note that the energy is not transferred across the boundary of the isolated system, and energy is transformed within the system from one type of another. So again, as the potential energy decreases, the kinetic energy increases, and as the kinetic energy increases, the potential energy decreases. In the case of the falling book, the transfer mechanism is the work done on the book within the system by the gravitational force. Okay, let's okay, got distracted there, sorry. Let's see, the sum of kinetic and potential energies of the system equals the mechanical energy. So mu is the total of all types of potential energy. So the E mechanical is defined as the sum of the kinetic energy plus the potential energy. Because a system is isolated, the mechanical energy of the system is conserved. The change in mechanical energy is equal to zero. Again, if you have a decrease in potential energy, you'll have a equal increase in kinetic energy. This equation is a statement of conservation of mechanical energy for isolated systems with no non-conservative forces acting on it. Mechanical energy in such a system is conserved, and the sum of kinetic and potential energies remains constant. We write the changes in energy explicitly. So kinetic energy final minus kinetic energy initial plus a potential energy final minus potential energy initial all equals zero. You sum all those together and you get zero. So looking at the final and the initial states, you get the final kinetic energy plus the final potential energy has to equal the initial kinetic energy plus the initial potential energy. Okay, let's see. Lost my place. Okay, for gravitational situation, of the following book, we write the following. Now those are the two that's like the equation just above it. The kinetic energy final plus the potential energy final equals the initial kinetic energy plus the initial potential energy. So that's the equation. As the book falls to Earth, the book Earth system loses potential energy and gains kinetic energy. The total of the two types of energy always remains constant. E mechanical plus E internal equals E total initial equals E total final. If non-conservative forces are acting within the system, the mechanical energy is transformed to internal energy. If non-conservative forces act on the isolated system, the total energy of the system is conserved. However, the mechanical energy is not conserved. The expression of the conservation of energy of the system is the total change in the system is equal to 0. The total change in the energy of the system is equal to 0. So the E of the system includes all kinetic, potential, and internal energies. This equation is the most general statement of the energy version of the isolated system model. Associated with this most general equation for isolated systems are new transformation mechanisms. Example, the non-conservative forces, warming of sandpaper, chemical reactions, exploding firecracker, and nuclear reactions, operation of nuclear reactor. Okay, let's look at a rock of mass M is dropped to the ground from a height h. A second rock with mass 2m, in other words, twice the mass, is dropped from the same height. When the second rock strikes the ground, what is its kinetic energy? Now, pay attention to the question. What is its kinetic energy? Is it twice that of the first rock? Is it 4 times that of the first rock? Is it the same as that of the first rock? Half as much as that of the first rock? It's impossible to determine. Now we're talking about kinetic energy. If we were talking about velocity, ignoring air resistance, it would be the same. But we're not talking about velocity. We're talking about kinetic energy. And it happens to be twice that of the first rock. Okay? The more massive rock has twice as much gravitational potential energy associated with it compared with that of the lighter rock. Because mechanical energy of an isolated system is conserved, the more massive rock will arrive at the ground with twice as much kinetic energy as a lighter rock. If it had twice as much potential energy, it's going to have twice as much kinetic energy when it lands. Okay. Now, 3 identical balls are thrown from the top of a building, all with the same initial speed, as shown in the figure. The first is thrown horizontally, the second at some angle above the horizontal, and the third at some angle below the horizontal. Neglecting air resistance, rank the speeds of the balls at the instant each hits the ground. And I didn't give you enough time to think about it. Sorry about that. The truth is, all the velocities are the same. V1 equals V2 equals V3. The first and third balls speed up after they are thrown, whereas the second ball initially slows down, but then speeds up after reaching its peak. The paths of all 3 balls are parabolas, and the balls take different time intervals to reach the ground because they have different initial velocities. All 3 balls, however, have the same speed at the moment they hit the ground because all start with the same kinetic energy and because the ball-earth system undergoes the same change in gravitational potential energy in all 3 cases. All right. Let's look at an analysis model, energy of the isolated system. We have the system boundary. Inside we have kinetic energy, potential energy, and internal energy. The total amount of energy in the system is constant. Energy transforms among the 3 possible types. So imagine you have identified a system to be analyzed and have defined a system boundary. Energy can exist in the system in 3 forms: kinetic, potential, and internal. Imagine also a situation in which no energy crosses the boundary of the system by any method. Then the system is isolated. Energy transforms from one form to another in energy conservation. And the energy conservation equation becomes the change in the energy of the system is equal to 0. If no non-conservative forces act within the isolated system, the mechanical energy of the system is conserved. So if no non-conservative forces act on it, E mechanical equals 0. What's a non-conservative force? Something like friction. So that would change. So examples are an object in free fall. Gravitational potential energy transforms to kinetic energy. That's ignoring wind resistance. A basketball rolling across a gym floor comes to rest. Kinetic energy transforms to internal energy. Delta K equals the change in internal energy plus the change in internal energy equals 0. A pendulum is raised and released with an initial speed. Its motion eventually stops due to air resistance. Gravitational potential energy and kinetic energy transform to internal energy. A battery is connected to a resistor. Chemical potential energy in the battery transforms to internal energy in the resistor. So the chemical potential energy plus the internal energy of the resistor equals 0. Probably also the battery too. It probably gets warm as it's transferring electrons. Now let's look at example 8.2, a ball in free fall. A ball of mass m is dropped from height h above the ground as shown in the figure. Neglecting air resistance, determine the speed of the ball when it is at a height y above the ground. Choose the system as the ball and earth. Now we're not looking for values here. We're just looking for an equation. So we conceptualize this as follows. The figure in our everyday experience with falling objects allows us to conceptualize the situation. Although we can readily solve this problem with the techniques of chapter 2, let's practice using an energy approach. So we categorize this as follows. As suggested in the problem, we identify the system as the ball and the earth because there is neither air resistance nor any other interaction between the system and the environment. The system is isolated, and we use the isolated system for energy model. The only force between members of the system is the gravitational force, which is conservative. So we analyze this as follows. Because the system is isolated and there is no non-conservative forces acting within the system, we apply the principle of conservation of mechanical energy to the ball-earth system. We apply at the instant the ball is released, its kinetic energy, K initial, equals 0, and the gravitational potential energy of the system is mgh. When the ball is at a position y above the ground, its kinetic energy, K final, equals 1/2 mv final squared, and the potential energy relative to the ground is gravitational potential energy final is equal to mgy. So we write the appropriate reduction of the conservation of energy equation, noting that the only types of energy in the system that can change are kinetic energy and gravitational potential energy. So the delta K plus delta UG, so the kinetic energy plus the gravitational potential energy equals 0. Now we substitute for the energies. The initial kinetic energy is 0. So we have 1/2 mv final squared minus 0. But we do have both a y and a g. If you look at the figure, you see that the y is not at the 0 point. It's y above the y equals 0 point. So there is a delta, mgy minus mgh, where mgh is the initial height. Let's see, solve for v final. You subtract, we can take out mg mg. If we transfer it to the other side, we get a minus mgy plus an mgh. We just reverse those and pull out the mg. We get mg times open paren y minus h. Now we divide both by 2m, and the m's cancel. So we end up with 2g times h minus y, and then if we take the square root of both sides, we get 2g, the square root of 2g minus hy. The speed is always positive. It has to be positive. It's under the square root. If you had been asked to find the ball's velocity, you would use the negative value of the square root as the y component to indicate downward motion. Okay. Now, find the speed of the ball again at height y by choosing the ball as the system. Again, we categorize, in this case, the only type of energy in the system that changes is kinetic energy. A single object that can be modeled as a particle cannot possess potential energy. The effect of gravity is to do work on the ball across the boundary of the system. We use the non-isolated system for energy model. Write the appropriate equation for the conservation of energy equation. That's delta K, change in kinetic energy, is equal to work. We substitute for the initial and final kinetic energies and work. Initial kinetic energy is 0. We have m1/2 mv final squared, and we have the force of gravity times the delta r, which is the y, since it's only in the vertical direction. We solve for v, and we get the same. The final result is the same regardless of the choice of the system. And in your future problem solving, keep in mind that the choice of system is yours to make. Sometimes the problem is much easier to solve if a judicious choice is made as to the system to analyze. Now, what if the ball were thrown downward from its highest position with a speed v initial? What would its speed be? What would its speed be at height y? Well, we have to include an initial velocity component. If the ball is thrown downward initially, we would expect its speed at height y to be larger than if simply dropped. So you make your choice of the system, either the ball alone or the ball and the earth. You should find that either choice gives you the following result. You just have to account for the initial velocity. That looks like a lot like, if you recall our equations of motion, v final squared equals v initial squared plus 2g delta y. Remember that? It looks like the same equation. Solve for v final. Now, let's look at an example, a rather complicated example. We'll go through it. You're part of a stage crew for a theatrical company and are designing an apparatus to support an actor of mass 65 kilograms who is to fly down to the stage during the performance of a play. You attach the actor's harness to a 130 kilogram sandbag by means of a lightweight steel cable running smoothly over 2 frictionless pulleys as in the figure. You need 3 meters of cable between the harness and the nearest pulley so that the pulley can be hidden behind a curtain. Now, for the apparatus to work successfully, the sandbag must never lift above the floor as the actor swings from above the stage to the floor. That is called the initial angle that the actor's cable makes with the vertical theta. What is the maximum value theta can have before the sandbag lifts off the floor? Now, we must use several concepts to solve this problem. Imagine what happens as the actor approaches the bottom of the swing. At the bottom, the cable is vertical and must support his weight as well as provide centripetal acceleration of his body in the upward direction. At this point in his swing, the tension in the cable is the highest and the sandbag is most likely to lift off the floor. Now, looking first at the swinging of the actor from the initial point of to the lowest point, we modeled the actor and the earth as an isolated system for energy. We ignore air resistance, so there is no non-conservative forces acting. You might initially be tempted to model the system as non-isolated because of the interaction of the system with the cable, which is in the environment. The force applied to the actor by the cable, however, is always perpendicular to each element of the displacement of the actor and hence does no work. Therefore, in terms of energy transfer across the boundary, the system is isolated. Okay, so, oh, you know what? I apologize. I didn't advance when I was reading that, but I'm not going to go back and change it. Okay, we first find the actor's speed as he arrives at the floor as a function of the initial angle theta and the radius r of the circular path through which he swings. We use the particle model by choosing a particle point on the actor's body. From the isolated system model, we make the appropriate reduction of the conservation of energy equation for the actor Earth system. Delta K equals delta UG. So the kinetic energy plus the gravitational potential energy must equal 0. Let Y initial be the initial height of the actor above the floor, and V final be his speed at the instant before he lands. Notice that K initial equals 0. The initial kinetic energy equals 0 because the actor starts from rest. Insert the energies into the equation and solve for the final speed of the actor. So we have 1/2 the mass of the actor times the final velocity squared minus 0 because his initial kinetic energy was 0, and we have the potential energies, the mass of the actor times gy final minus the mass of the actor times gy initial. All of that has to equal 0. Well, the mass cancels in all of this if you subtract the mgy final and minus mgy initial to the other side, you get and then divide by 2 over m to isolate the v squared. You get 2g times y final minus y initial, and then when you the y final minus y initial is r minus r cosine theta, r times 1 minus cosine theta. In other words, the r cosine theta is like about where his sword is. Now r is all the way to the bottom, so you're looking at what y initial equals that r cosine theta equals the r cosine theta term. Let's see, and so v squared is equal to 2g times r times 1 minus cosine theta. Look at the geometry and you should understand it. Now, focus on the instant the actor is at the lowest point. Because the tension in the cable is transferred as a force applied to the sandbag, we model the actor at this instant as a particle under a net force. Because the actor moves along a circular arc, he experiences at the bottom of the swing a centripetal acceleration of v final squared divided by r directed upward. Now, apply Newton's second law for the particle under a net force model to the actor at the bottom of its path, using the free body diagram in the top figure as a guide, and recognize the acceleration as centripetal. So some of the forces in the y direction are the tension minus the mass of the actor times gravitational acceleration. And that's also the mass times acceleration is mass of the actor times v final squared r. Remember, the acceleration is v squared over r. Now let's solve for t. So t is equal to, you subtract mass of the actor times g from both sides, you get T equals mass of the actor times gravitational acceleration plus the mass of the actor times V final squared over R. Now, finally, notice that the sandbag lifts off the floor when the upward force exerted on it by the cable exceeds the gravitational force acting on it. The normal force from the floor is 0 when that happens. We do not, however, want the sandbag to lift off the floor. The sandbag must remain at rest, so we model it as a particle in equilibrium. A force T is transmitted by the cable to the sandbag. If the sandbag remains at rest, but is just ready to be lifted off the floor, if any more force were applied by the cable, the normal force on it becomes 0, and the particle in equilibrium model tells us that the tension equals the mass of the bag times gravitational acceleration, as in the bottom figure, the bottom the diagram. Now, if we solve for T, we get the mass of the bag. Let's see, is that the third? That's the third, yeah. So if we substitute the V final, we get this equation at the bottom. M, mass of the bag times gravitational acceleration equals the mass of the actor times gravitational acceleration plus the mass of the actor times the centripetal force. And I think that's right, that there is no squared term there. We solve for cosine theta, and we get, we solve for theta and substitute the given parameters, you get 60 degrees. You work it all out, you'll get the cosine theta equals 0.5, so theta equals 60 degrees, cosine of 60 equals 0.5. Here we had to combine several analysis models from different areas of our study. Notice that the length R of the cable from the actor's harness to the leftmost pulley did not appear in the final algebraic equation for cosine theta. Therefore, the answer is independent of R, the radius, the length of the cable. All right. Now, the launching mechanism of a popgun consists of a trigger release spring. The spring is compressed to a position YA, and the trigger is fired. The projectile of mass M rises to a position YC above the position at which it leaves the spring, indicated in the figure as position YB equals 0. Consider a firing of the gun for which M equals 35 grams, 0.035 kilograms, YA equals negative 0.12 M, that is below the Y equals 0 point, and YC equals 20 meters. That's pretty high, not true to scale in the figure. Neglecting all resistive forces, determine the spring constant. Okay, well, let me go back. Imagine the process illustrated in parts A and B of the figure. The projectile starts from rest at A, speeds up as the spring pushes upward on it, leaves the spring at B, and then slows down as the gravitational force pulls downward on it, eventually coming to rest at point C. Notice that there are two types of potential energy in this system, gravitational and elastic, or spring potential energy. We identify the system as the projectile, the spring, and the earth. We ignore both air resistance on the projectile and friction in the gun, so we model the system as isolated for energy with no non-conservative forces acting. So we have the kinetic energy plus the gravitational change of gravitational potential energy plus the change in spring potential energy all have to equal 0. Now, since we're looking at it from before the trigger is loaded, when the ball is on the spring, its kinetic energy is 0. When it reaches the top of its flight, the kinetic energy is 0. So again, because the projectile starts from rest and its kinetic energy, its initial kinetic energy is 0, we choose the 0 configuration for the gravitational potential energy of the system to be when the projectile leaves the spring at B. For this configuration, the elastic potential energy is also 0. After the gun is fired, the projectile rises to a maximum height yc. The final kinetic energy of the projectile is 0. From the isolated system model for energy, we write a conservation of mechanical energy equation for the system being between configurations when the projectile is at points A and C. So we substitute for initial and final energies. Again, kinetic energy is 0. For the initial and final cases, that's why we have 0 minus 0. We have mgy C minus mgy A for the potential energy, and we have spring potential energy initial is 1/2 kx squared. There is no spring potential energy when it reaches the top, so the final is 0. We solve for k, and we substitute numerical values, and you get 958 Newton meters. I think I actually got a little bit different value because I didn't include the little 1.2 meters because I took it as 0, but no, I'll go with what the author says. Okay, let's see. Find the speed of the projectile as it moves through the equilibrium position B of the spring. So the kinetic energy, the change in kinetic energy plus the change in gravitational energy and the change in spring potential energy all equals 0. So now we do have at point B 1/2 mv b squared minus 0 because the initial kinetic energy was 0. We have, since y is 0, we have only mgy a, and we have the 1/2 kx squared. The spring is fully extended, so the final is equal to 0. All of that has to equal to 0. The energy of the system as the projectile moves through the equilibrium position of the spring includes only the kinetic energy of the projectile. Both types of potential energy are equal to 0 for this configuration of the system. Write the conservation of energy equation for the system between configurations of which the projectile is at points A and B. Now you substitute the initial and final energies. That's the equation we already have up there. Solve for B. VB equals kx squared divided by m plus 2gy. And then substitute the numerical values, and you get 19.8 meters per second. This example is the first one we have seen in which we must include 2 different types of potential energy. Notice in part A that we never needed to consider anything about the speed of the ball between points A and C, which is part of the power of the energy approach. Changes in kinetic and potential energy depend only on the initial and final values, not on what happens between the configurations corresponding to these values. Okay, now this ends our discussion of the isolated system analysis model. Next, we will discuss section 8.3, situations involving kinetic friction.